Know that during World War II, German spies had a plan to destroy the beautiful intake towers of Hoover Dam? What do you think would have happened if their plan had succeeded? Hoover Dam's power production capability is huge. There are 17 turbines and generators arranged in this U-shaped power production facility. Let's assume that the generators have produced electricity. This electricity reaches transmission towers. Did you notice something strange here? Why are these transmission towers dangerously inclined? Why didn't they install the towers vertically? If they had installed them vertically, the distance between the cable and canyon would have been reduced. The canyon walls have metallic properties, and such a high voltage line close to the rock would lead to electrical arcing. This is why the engineers chose to erect the power transmission towers inclined. Now, it's time to learn more about the turbines and generators of the Hoover Dam. Hoover Dam uses a type of turbine called Francis turbine. Please take a look at the size of this scroll case. The big question is, how can such giant turbines and generators be installed inside this power generating facility? If you've ever visited Hoover Dam, you might have noticed a weird-looking tower and pulley cable arrangement. This beautiful machine, a cableway, did the impossible task of installing turbines and generators. It looks weird, right? How are all these wheels able to stand straight without falling down? You can see that all these main wheels are connected via a carriage. These tiny support wheels and support wires prevent them from falling down. Now, the genius part. These two drums make this arrangement move left or right using simple cable pulling. The ends of these cables are attached to the carriage. This animation shows how it's moved left. Movement to the right is achieved in the opposite way. Now, about the hoisting mechanism. An additional drum was used for this purpose. You can see the clever passage of the cable around the pulleys. You can also predict what happens to the hoist when the drum rotates. The 3 cable drums we just saw are kept inside a hoist house. This is how they transported material to the turbine region. And this hoist mechanism is still getting used. Sheer genius, right? After the transportation, a large gantry crane was used to help assemble and install the generators, rotor, stator, and other heavy components. The Francis turbine runner blades have a beautiful shape. The runner is surrounded by a spiral casing. Water initially travels via this spiral casing, and a few guide vanes inside the casing guide the water properly into the runner. When the high-energy water interacts with the Francis turbine blade, magic happens. The runner spins. To understand how the runner spins, let's follow a few fluid particles. You can see that these particles are taking a happy journey, flowing around the Francis turbine runner blades. Interestingly, this is a clear case of airfoil action. High pressure will be generated at one side of the blade, while low pressure is generated at the other. Obviously, this pressure difference can turn the turbine, but the journey of fluid particles is not over. Just before they leave, they hit the bucket-shaped portion of the turbine blade, generating pure impulse force. Both these forces, the lift force and the impulse force, make the runner turn. This is how energy is extracted from water at Hoover Dam. At the outlet of the turbine, water loses both the kinetic energy and the pressure energy. This beautiful mechanism is the governing mechanism of Hoover Dam's turbine. Can you predict what will happen if you turn this ring? Yes, you are right. The clever mechanism will close the guide vanes and the water flow rate will be reduced. The governing mechanism regulates water flow by adjusting the angle of the guide vanes. If the guide vanes are more open, the water flow rate to the turbine will be higher, and thus more power will be produced. If the power demand is low, the guide vanes can be closed to decrease the water flow rate. This enables precise power generation control based on demand. Water exiting through the draft tubes of Hoover Dam is diverted downstream to irrigate approximately 250,000 acres of desert land. Now, if you connect this spinning turbine to a generator, we are done. The electricity is in production. If you observe the generator, you'll see that both the rotor and the stator are just copper coils. No permanent magnets are used here. However, the rotor needs an electricity supply to generate magnetic fields. This current is supplied by an exciter. The exciter uses a permanent magnet stator. This means when the water force turns the exciter rotor, it will produce electricity. This electricity is fed to the rotor coil of the generator. The generator rotor can now produce a magnetic field, and the magnetic field will cut the stator coils. The result is power production at the stator side. Now it's time to transmit this electric power. But before that, we should go through the most important part of this video. How does the water from the reservoir reach the turbine? Did you notice a long pipe connecting the turbine and reservoir? This is known as penstock. Construction of these penstock lines was the most challenging and interesting phase of the Hoover Dam project. Using the cableway, workers were lowered into these giant holes. Their main duty was to drill the holes for the dynamite. Then it was time for the dynamite's controlled explosion. The explosion broke up the rock, ensuring efficient excavation. To clean up the tunnel, the workers used power shovels, conveyor belt type mucking machines, and even manual removal of material. This way, a giant hole was formed vertically. At the horizontal side of the penstock tunnel, the work was much easier. The entire geometry of the penstock system is shown here. The trucks and drilling jumbos entered the horizontal section via an access tunnel. Ultimately, the horizontal and vertical tunnels had to join perfectly.
This is how the tunnels look after the complete soil removal.
Later, this tunnel was lined with concrete. Could this concrete tunnel be used as a penstock? Theoretically, yes, but the high-speed water that comes down will have a huge impact force on this concrete layer, which means the concrete will erode over time. This is why engineers use steel lining for the penstock. To construct the penstocks for Hoover Dam, a specialized fabrication plant was set up near the dam site. The penstocks were made from steel plates, rolled using a giant press. 3 such plates were welded to form large pipes. The steel cableway we saw at the beginning of the video was commonly used to lower and position the penstock sections and other large components into the dam's tunnels. Specially designed trailers waiting at the access tunnels carried them inside the tunnels, and the pieces finally got connected. Pressure pins were used to form a continuous connection between the intake tower and the turbines and outlet valves. The AC power generated in the stator is then converted to a higher voltage using transformers for efficient, long-distance transmission. The high-voltage electricity is transmitted through power lines to the grid, where it supplies homes, businesses, and industries. The beautiful intake towers we saw in the beginning of the video in fact collect water from the reservoir and transfer it to the penstock. Each intake tower is equipped with 2 gates. You can see the way water flows when the gates are open. Interestingly, the operators can close these gates and block water flow for the maintenance of penstock or turbines. Here comes the question. Why do we want an intake tower at all? Why can't we collect the water directly like this? Let's do an experiment to understand the need of the intake towers.
Penstock with an intake tower versus a penstock without an intake tower. Let's see what happens when we open these penstocks. You can see all the debris are moving towards whole area and the whole of this penstock getting stuck, but there is no such issue in this penstock with intake tower area.
This means, had the German spies succeeded in destroying the intake towers, the water flow to the turbines would have ceased immediately. Without damaging a single turbine or generator, the spies would have been able to cease the power production capability of Hoover Dam, the biggest power production facility of that time. You've understood a lot about Hoover Dam's power production capabilities. Let's have a journey along with a few water particles and revise all the stages in power production. The water particles enter the intake towers from different regions of the reservoir. As they come down, their velocity increases. After passing the intake towers, it's time to have a long journey along the penstock. Now, the penstock gets divided into 4 pieces. A few particles enter this particular penstock. After this long downward journey, the particles attain a good speed. The high pressure and high speed water stream now enters the runner of the Francis turbine. You know the details of how they turn the turbine. At the exit of the turbine, the water stream loses its pressure and kinetic energy and exits via a draft tube. The water stream's energy drop is the turbine's energy gain. The turbine transfers this energy to the generator and we get electricity.
This power plant is noisy. I hope you see more such videos in the